Hello guys, welcome back to chapter 4, and today is lesson 4.1 where we're going to learn how to graph polynomial functions. So all of chapter 4 happens to do with polynomials. It's actually one of my favorite chapters in the book, and hopefully you guys will like it too. All right? So before we graph these polynomial functions, we first have to define what a polynomial function is. Okay? So a polynomial is a monomial or sum of monomials. And you might be asking, well, what is a monomial? So I really should have defined that first. A monomial is a number a variable or the product of one or more variables with a whole number exponents. All right, so let's look at this. Monomial is either a number, a variable, or the product of one or more variables with a whole number exponents. So let's do examples of monomials here. Okay, so a number, 7, that's a monomial. Okay, a variable, x, that's a monomial. The product of a number and one or more variables, so maybe 5xy squared, that's a monomial. You have a number, you have variables with whole number exponents. That's very, very important. Your exponents must be whole numbers. So let's write that down. Exponents must be whole numbers. And if you forgot, whole numbers look like this: 0, 1, 2, 3, etc. They are they are positive or zero, and they cannot include fractions or decimals. So whole numbers. They're similar to integers. The only difference between whole numbers and integers is that whole numbers cannot be negative, while integers can. Okay? So let's keep that in mind. Anytime you have exponents with monomials and also with polynomials, they have to be whole numbers. Okay? And then a polynomial is a monomial or a sum of monomials. So for example, examples of polynomials. You could have 3x plus 3, for example. That's a polynomial. It has two monomials, right? Something like 2x squared plus x minus 2. That's a polynomial. This is a monomial, this is a monomial, and this is a monomial. Okay? Something like x to the 4th plus 2x squared plus 7. That's also a polynomial. This is a monomial, monomial, monomial. All right? So remember, your exponents must be whole numbers, And the coefficients, this is also important, the coefficients must all be real numbers. So what is a coefficient? A coefficient is the number in front of the x variable. So for example, here we don't see it, but it has a coefficient of 1. This has a coefficient of 2. This has a coefficient of 1. This has a coefficient of 1. This has a coefficient of 2. And by the way, these constants at the end really, we just don't write it, have an x to the 0 term here. X to the 0. Because what, guys, is x to the 0? Anything to the 0 power is 1. So if I do x to the 0, that's just 1. 1 times 7 is just 7. So what you need to know is that constants have this exponent, also called a degree, of 0. All right, and so 7 technically is a coefficient. Again, that has to be a real number. 2 is technically a coefficient. That's a real number. And 3 is a coefficient. That's a real number. So coefficients are all real numbers. And the first term, first we have to put these in standard form. Let's talk about standard form. Standard form of a polynomial is when your polynomial is ordered in descending order. Descending order. So let's say I have this polynomial. Okay? This is a polynomial, however, it is not in standard form. For it to be in standard form, you need to put the first term that has the biggest exponent, the biggest degree. Well, it happens to be this guy. So this term has to go in the front, negative 7x to the third. And then we descend from there. So 1 less than 3 would be this. 1 less than 2 would be 1, and so on. This one is in standard form. Now you could be missing terms. For example, you may have a term to the third power. You may not have an x squared term. You may not have a constant, for example. This may be your polynomial, negative 7x to the third plus 3x. That's fine. And it is in standard form because you're ordering it from smaller to largest. Now, when you have this polynomial in standard form, this very first term is going to contain the degree of the polynomial. The degree of the polynomial is the biggest exponent there in your entire polynomial. So obviously 3. So the degree of this polynomial is 3. And it's also going to contain the leading coefficient. Remember I mentioned what coefficients were? It's those numbers in front of your x's. Well, here, this negative 7, that is your leading coefficient for the entire polynomial. Okay? So a lot of information is obtained from that first term, again, after it's in standard form. All right, let's take a look at a little table and get a little bit of look at some of the names of the different types of polynomials, because there are different types of polynomials, and it depends on a couple of things. Right now we're going to look at the degree of the polynomial. So we're going to classify these polynomials by degree. So let's just do our little table. And I need one more line here. I never really get these right. I always do one too few of these rows. All right, 1, 2, 3, 4, 5. 1, 2, 3. Okay. Let's go ahead and do this. All right. So here we are going to write the degree. Now remember, degree has to do with the exponent. Then we're going to talk about the type, and this is based strictly on the degree. Then we're going to do standard form so you can see what it looks like, and we'll put an example. All right, let's take this one. Okay, so a degree of 0, and we already touched on this. We said that constants have a degree at 0, right? Because you can see a constant like 6 really can be written as 6x squared, where that's a 1, and 1 times 6 is 6. Yeah, we just don't write that. So whenever you look at a polynomial or a monomial that has a degree of 0, it is a constant. And the standard form is f of x equals a sub 0, just the term, again being a constant. And an example would be, for example, f of x equals negative 14. That is a constant. Okay, degree of 1. A degree of 1, by now you should know, is a line. It's a linear. And that's going to look like something like this. A sub 1 of x. You're going to have the x term in there. The x to the first term, by the way, plus a sub 0. So you could have something like this. That is a line. Yeah? Happens to be in slope-intercept form, where negative 7 is the y-intercept and your slope is 5. That's a linear. And I did forget one of these. I knew it. All right. There we go. If you have a degree of 2, again, should be very familiar by now. You have a quadratic. So the standard form is something like this: a sub 2x squared plus a sub 1x plus a sub 0. So an example of a quadratic could be something like 2x squared plus x minus 9, right? You got your square term, you got your x to the first term, and you have your constant. Number 3, if the degree is a third degree, it is going to be called a cubic. And you guessed it, that means there's an x to the third degree, x to the third power term. So we have a sub 3 x to the third plus a sub 2 x squared plus a sub 1 x plus a sub 0. So something like this: x to the third minus x squared minus plus 3x. Now, for example, this one in particular doesn't have a constant. That's okay. It is still a third degree polynomial because the biggest degree is 3, so it is a cubic. It just only has 3 terms, and that's perfectly fine. Fourth degree is going to be called a quartic. So we just add a fourth degree to the term to the front that has an x to the fourth. And we could have x to the thirds, x squares, x's, and constants. So here's an example of this one. X to the fourth plus 2x minus 1. Again, you're missing an x to the third term. You're missing an x squared term, but that's fine. You could have easily made it like this. These are all quartics, so it could easily be x to the third plus 5x squared plus 2x minus 1. It could have as few as one term, and it could have as many as 5 terms, right? Because it could just be, believe it or not, that. A monomial, just one term, but it is a quartic, and that, so it could have one term, that's the least number, and it could have 1, 2, 3, 4, 5 terms. That is the most number of terms a quartic could have. Okay, and everything in between will work. All right, let's move on to example 1. So here we go. All right, we're going to determine if the function is a polynomial. So we have to check the rules for what a polynomial is, all right? Make sure it meets those criteria, because not everything is a polynomial. Now, if it is a polynomial, if so, then you're going to write it in standard form. And you're going to give me some of its characteristics. You're going to state its degree, its type, and the leading coefficient. All right, so here we go. Here's example A. They're going to give you f of x equals negative 2x to the third plus 5x plus 8. Now the question is it a polynomial? All right, well, one of the things that have to be true is that your exponents have to be whole numbers. So this is 3, this is to the first, and this is your 0, right, because it's your constant. So 3 is a whole number, 1 is a whole number, 0 is a whole number, so it passes that test. And the other thing is that the coefficients in front must be real numbers. In other words, there can't be the square root of a negative in there, and there can't be a little I anywhere. So this is a real number, that's a real number, that's a real number. So both of these tests are passed. So our answer is yes, it is a polynomial. The next thing we do is write it in standard form. Well, this guy is already in standard form. It's descending order, 3, 1, 0. So I'm just going to rewrite it, but it has already been done for you. So that's awesome. Okay, state its degree. So again, degree, this is coming from that very first term. After you put it in standard form, the degree is the exponent in that term, so that's a third degree polynomial. The type, because it is a third degree polynomial, we call it a cubic. And the leading coefficient, again, having to do with that first term, is this thing in front of the x, which is negative 2. So we've got all our information there. Let's take a look at another one. Again, the same questions are being asked, just a different problem. So here we have g of x. G of x equals negative 0.8 x to the third plus the square root of 2 x to the fourth minus 12. All right. Again, first question is it a polynomial or not? So let's check the exponents. The exponents are 3, 4, and this is 0. So yeah, as far as the exponents are concerned, we're good. They're all whole numbers. Then let's check the coefficients. We've got this, this, and that. Negative 0.8, that's a real number. Square root of 2, that's a real number. And negative 12, that's also a real number. So we pass both tests. This is a polynomial. And now we do need to order this one. This one is not in order. So we put the term with the biggest exponent first. That's going to be square root of 2, x to the 4th. Then we have minus 0.8, x to the 3rd, minus 12. All right? The degree of this guy, again, this is all coming from this first term here. The degree is 4. That means that the type is a quartic. And the leading coefficient is the square root of 2. Now remember, if this was the square root of a negative 2, this would not be a polynomial because that would have an imaginary number, not a real number, as a leading coefficient. Or if you had an I anywhere here, this would not be a polynomial. Okay? All right, moving on. Moving on, moving on. Let's try this one. Here we have h of x equals negative x squared plus 7x to the negative 1 plus 4x. All right, so our first step is to check our exponents. We have a 2, a negative 1, and this happens to be a 1. Are they whole numbers? No, negative 1 is not a whole number. So this is not a polynomial because negative 1 is not a whole number. Remember, whole numbers are 0, 1, 2, 3, 4, 5, etc. No negatives. Now, a little side note in big ideas, you might see 7x to the negative first written as 7 over x to the positive 1. Remember, we can do that. We can change a negative exponent to a positive by putting it in the denominator. So if you see this as a term, for example, in big ideas, that will also disqualify it from being a polynomial, because when you have 1 over x to the first, that's equal to x to the negative 1. And we go back to the same situation. Negative 1 is not a whole number. So just be on the lookout. You can see it like that. Sometimes you'll see it like that. It's the same thing. Not a polynomial. All right, and let's do D. Here we have k of x equals x squared plus 3 to the x. All right, so again, we're going to check our exponents. We have a 2 and an x. Are they both whole numbers? Well, 2 is a whole number. X, I have no idea what it is. So no, because the exponent is not a whole number. And oh yeah, by the way, this base has to be a variable. So let's add that in there, and we call that the base of the exponent. The base is not a variable. So it cannot be just a value, it must be a variable. It could be x to the 3rd, but it can't be 3 to the x. All right? Okay, moving on. This is so much fun. I don't know about you guys, but I'm really enjoying this. Example 2, evaluating. This is when you bring out that old calculator that's sitting next to you. Unless you really like to do arithmetic, in which case, go ahead, knock yourself out. but most people will probably use a calculator. So here we have an evaluate, and you're giving you f of x equals 2x to the fourth minus 8x squared plus 5x minus 7, and they want you to evaluate it when x equals 3. Well, this you know how to do. This is super simple stuff, baby stuff. So basically what they're asking you to do is go into this polynomial up here, wherever you have an x, plug in a 3, and tell me what the value is. So we're going to call that f of 3, the value of the function at 3. That is going to equal 2. My x is now 3, so this will be 3 to the fourth, excuse me, minus 8. That's going to be 3 squared plus 5 times 3 minus 7. All right? And this is where you need to remember your order of operations, guys. Please remember that. Everything in math is done using order of operations, so don't just ignore it and try to do your thing. You must do parentheses and then exponents. So we're going to do that. That's an exponent. That's an exponent. Let's take care of that first. So 3 to the fourth, that is going to be 81. We're going to be left with 2 times 81 minus 8 times 3 squared, that is 9. And this is 5 times 3 minus 7. So we've done our exponents. Now we're going to go ahead and do multiplication. So 81 times 2, that is going to be 162. Let's just rewrite this. This is going to be minus 72 plus 15 minus 7. And once you have done all that, now you're ready to add, subtract again from left to right, order of operations, and that'll give you 98. Okay, so easy enough. All right. Now we're going to go to a graphic that's in your book. It's also in the notes that you find in Schoology. Obviously, I'm not going to try and draw this because they do it so much better. So I'm going to go ahead and just put it here so I can explain it a little bit. Let's make this a little bit bigger. All right. So we're looking strictly at the end behavior of polynomial functions. Remember what end behavior is. As x gets really big, what happens to the function? As x gets really small, again, what happens to the function? That's known as end behavior. Notice that the stuff in the middle is little dotted lines. We really don't care. We really honestly do not care at this point what's going on in there. We just know something's going on in there, but we only care about these extremes, right? When x is really small, when x is really big, etc., etc. So you have 4 possibilities of how this can go, depending on 2 things. These things highlighted in yellow, depending on the degree of the polynomial and depending on the sign of the leading coefficient. Okay? Now for these 2 down here, I'm going to pick my favorite even degree polynomial. You guessed it, a quadratic. Now if you remember quadratics, they can do one of 2 things. They can open up or they can open down. They open up when it is a positive coefficient, yeah? And they open down when it is a negative coefficient, leading coefficient, in front of the x squared. And we've done that. We've done it a million times. So I'm going to go ahead and generalize my experience with quadratics to all even polynomial functions. So whether it's a quadratic or a quartic or a 6th degree polynomial or an 8th degree, whatever even number you like, they're going to behave similarly at the end. Now again, in the middle, who knows what's going on in there? But at the end, they will behave the same. So if you have an even degree polynomial and the leading coefficient is positive, your end behavior is going to be up and up. That means as x goes to negative infinity, the function goes to positive infinity. As x goes to positive infinity, the function still goes to positive infinity, up and up. That's if it's even and the leading coefficient is positive, like this. Similarly, if it's even and the leading coefficient is negative, we're going to go down and down. Again, doesn't matter what's going on in the middle. I don't care. But I know that at the very ends, at the very extremes, when x is getting very, very small or when x is getting very, very large, my function is going to go to negative infinity. So this one's pretty easy to memorize because, again, you can just go back and reference your favorite even polynomial, the quadratic function. Now, for odds, you can use a cubic function, which, looks like that. Or you could actually use a very simple odd function, which is a linear. Okay? So in our experience with lines, this is a line that has a positive slope. And by the way, positive slope means the leading coefficient is positive. And this is a line with a negative slope, which again means the leading coefficient is negative. And if you look at a line, let's make this, for example, the xy coordinate plane. As x gets bigger and bigger and bigger, the function gets bigger and bigger. And as x gets smaller, the function gets smaller. So an odd degree with a positive coefficient is going to have this behavior. Okay, down and up, down and up. If it was a positive cubic function does something like that. Now the negative one will flip around like this. So it's going to be the opposite. Instead of down and up, it's going to be up and down. Just like the line, up, this is going towards positive infinity, down, going towards negative infinity. So you do have to memorize that. You do have to know, depending on the degree and the coefficient, whether it's positive or negative, which way your end behavior is going. Just remember, if the degrees are even, you're either going to have both up or both down. And then when you have one of each, one going up, one going down, or one going down, one going up, you know your degree is odd. And then all you have to do is figure out whether it's positive or negative. And this is the positive one. This is the negative one. Okay? All right. All right, all right. Let's move on. Just a second. Okay, so let's now take a look at example 3. Describing end behavior. Sorry about that example. 3. Okay, so describe the end behavior. And this is without having to graph it. Oh, you know what? Before we go on, let me do a quick little table in case you want to memorize this. All right, we have up and up. We have down and down. We have down and up. And we have up and down. What does that mean? Okay, so this is whether it is positive or negative, right? And this is whether the degree is even or odd. So once again, an even degree that's positive is up and up. An even degree that is negative is down and down. An odd degree that is positive is down and up. And an odd degree that is negative is up and down. So if you want to memorize that little chart, go for it. Easy peasy. Okay, so let's go back to this. Describe the end behavior of f of x equals negative 0.5 x to the 4th plus 2.5 x squared plus x minus 1. All right, first thing you got to check, is this a polynomial? Yep. Is it in standard form? 4, 3, 4, 2, 1, 0. Yep, it's in standard form. Okay, so now we're going to look strictly at this first term. What is the degree? Well, the degree here is the exponent, which is 4. So that's a fourth degree. And a fourth degree is even. Okay? Then we're going to look at the leading coefficient. And the leading coefficient is negative 0.5. So that is negative. And you are being asked, well, what's the end behavior? So we have even and negative. So even with negative is going to be this guy. So this is your end behavior, down and down. All right. So this is going to look probably something like that. Because it is a fourth degree. Fourth degrees kind of look like an M upside down. Remember, quadratics look like that. Fourth degrees kind of have that curvy look, the little M look. So it's going to open down and down. And then we're going to go ahead and describe our end behavior. As x goes to positive infinity, f of x goes to negative infinity. Remember, we're going, both of these are going to negative infinity. And as x goes to negative infinity, the function still goes to negative infinity, right? This one represents as x goes to infinity, to negative infinity, what happens to the function. This is as x goes to positive infinity, what happens to the function. All right? Okay, moving on to example 4. Here we have a graphing problem. So they want us to graph f of x equals negative x to the third plus x squared plus 3x minus 3. All right, first thing, is it a polynomial? Yep. Second thing, is it in standard form? Yes. There's a 3, 2, 1, and then a 0. Let me put this right there. Okay, so we have it in standard form, and it is a polynomial. So the first thing we can find here really quickly is the y-intercept, because remember, we want to graph this. So we want some points that are like pretty important. So where it crosses the y-axis, that's kind of an important thing. And the y-intercept is found by letting x equal 0. So if I let my x be 0, that's going to go to 0. That's going to go to 0. That's going to go to 0. And I'm going to be left with negative 3. So that means that this polynomial function is going to cross the y-axis at the point 0, negative 1, negative 2, negative 3, right there. That's its y-intercept. Okay? Now we're going to need to make a table of values. So let's do that. Table of values. And again, my favorite values, just because they're easy to work with and they're around where the it's just the nicer numbers to use. Negative 2, negative 1, 0, 1, and 2. Now remember something. This guy, this is a cubic function. You can tell because it's to the third power. This is not going to be symmetric like our quadratics. So when I start filling this out, the values here will not be the same ones that you get here. Okay, so you gotta plug every single one in. You can't get lazy on these. So we already plugged in 0 and we got negative 3, so we got that point. And then you're gonna plug in negative 2 and negative 1. There's my lovely chihuahua barking in the background. Oh my goodness, isn't that delightful? We're gonna put in these numbers for x and see what our values are. So let's begin, shall we, with negative 2. I'm going to go over here in the corner. So negative, and then we have negative 2 to the third plus negative 2 squared plus 3 times negative 2 minus 3. Again, we're plugging in negative 2. So do the exponents first. Negative 2 to the third, that's negative 8. But we want the negative of a negative 8, which is going to be a positive 8. Here we have negative 2 squared, that's positive 4. Here we have 3 times negative 2, that's negative 6 minus 3. So a plus 4, that's 12. 12 minus 6 is 6. 6 minus 3 is 3. So this guy right over here is 3. At negative 1, negative 2, I'm at 1, 2, 3. All right. Okay, let's do negative 1. So same thing, but I'm going to put a negative 1. Negative 1 to the third, that is also negative 1, but we have a negative of a negative 1, which will make it a positive. Negative 1 squared is positive 1. This will be minus 3, minus 3. 1 plus 1 is 2. 2 minus 3 is negative 1. Negative 1 minus 3 is negative 4. So at negative 1, I'm at negative 1, 2, 3, 4. All right, let's plug in a positive 1. So again, let me do it over here. We have a negative, and this is a positive 1 to the third plus positive 1 squared plus 3 times 1 minus 3. All right, 1 to the third, that's 1, but we have to put a minus in front. 1 squared is 1. 3 times 1 is 3 minus 3. So negative 1 plus 1, that's 0. Plus 3 is 3. Minus 3 is 0. So this one goes to 0. So at 1, we are at 0. And last but not least, we're going to put in a 2. So this is going to be 2 to the third plus 2 squared plus 3 times 2 minus 3. All right, so 2 to the third, that's 8, and you've got your minus out there. 2 squared is 4, so that's plus 4. 3 squared, 3 times 2, that's 6, and then minus 3. So negative 8 plus 4, that's negative 4. Negative 4 plus 6, that's 2. And 2 minus 3, that is negative 1. So at 1, 2, we are at negative 1. All right, well that looks lovely, right? But it is our table of values. Our next step is to obviously graph the points, which I already did. Graph points. And the third step is to connect your points with a smooth curve, because polynomials are smooth. Connect the points. Nothing sharp, nothing absolute value like. No, no, no. Connect the points with smooth curves. So again, to the best of our ability. Looks like this is doing this, then maybe something like that, maybe something like that. Again, this is just almost not really a sketch, because we do have some real points, but it's not exact. You know, we don't know if other things happen around here, but we kind of know it's going to go through those points. We know that much. And the last thing we need to do is check our end behavior. Make sure it's what we would think it would be. Now remember, we know how to predict end behavior because, you know, we're good like that. We know that if we look at the first term, in this case, this is an odd degree, right? It's a third degree polynomial, so it is odd and negative. And if you look at your little chart thingy, if we are odd and negative, this is our end behavior. And if you look at this, wow, look at that. It matches. The end behavior matches. So we are on the right track. We did do a pretty good job of graphing this. So good job, guys. Way to go. Okay? All right. Almost there. We have one last example. I know it's sad. Then we'll have to stop the video, but we can't do this forever. You know, the fun can't go on forever. All right, example 5. Example 5. Again, this is something that's coming from your book, so I'm just going to bring it right over. If you want to print it, it is in Schoology, and you can just easily print it out. But this is so much cooler the way they do it. Actually, you know what? No, I'm going to do it, and then we'll show their part. But we'll do it ourselves. We'll do it ourselves. Why not? We can make this cool too. So here we're going to sketch a graph. Sketch a graph of the polynomial function f that has the following characteristics with the following characteristics. All right, so they're going to go ahead and list these things. First thing, f is increasing when x is less than 0 and x is greater than 4. All right, so that's a little tidbit. It's like little clues they're giving you, and then you have to figure it out. F is decreasing when 0 is less than x, which is less than 4. Okay? Clue number 3. F of x is greater than 0 when negative 2 is less than x is less than 3 and x is greater than 5. Okay? And f of x is less than 0 when x is less than negative 2 and 3 is less than x is less than 5. Wow, that's a lot of information. So let's kind of see what they're actually telling us. We'll start with the things that are most obvious and move from there. All right, so I'm actually going to look at these two first. Because remember, when things change from being greater than 0 to being less than 0, that means they have crossed over the x-axis. Stuff has happened here. So these guys, wait for it, you know what they are, have to be x-intercepts because they are points where things change, where the function goes from being positive to, let's say, being negative. So let's first plot our x-intercepts. So stuff is happening between negative 2, so negative 1, negative 2, at negative 2, and at 3, and then at 5. These are 3 x-intercepts, negative 2, 3, and 5. And I'm getting them from here. Negative 2, 3, 5. And there they appear again, negative 2, 3, 5. So they are important. All right, let's do this first one. F of x is greater than 0. What that means is that my function is above the x-axis when I am between negative 2 and 3. Remember, this is negative 2, this is 3, and this is 5, in case you forget. So the function is positive between these two guys. Again, I don't know how high this goes. This could go like that. We have no idea, nor do we really care. We are sketching. Remember, sketching is just getting an idea. It's not the same thing as a graph where we have to graph it or plot it. We are sketching it. So it could be like that. It could be like that. It doesn't matter. But we know it's above the x-axis. And we also know it's above the x-axis when x is greater than 5. So that means something like that. Yeah? Now, we know, because they tell us, that it is below the x-axis. It's going to be negative when x is less than negative 2. So that means the thing is going that way. And is also, this is not a good pen, sorry about that. Let's try this one. And it's also negative between 3 and 5. So it is under the x-axis. Again, it could go like that. It could go like that. We have no idea. But we do have a general idea of what this looks like, right? We know that at -2, let's just make it look a little bit better. From here, it's down here. It goes from -2 to 3, then it goes down, and then it goes back up. That we know, that's its general look and feel. Again, the how high it goes, what the maximum point is, or what the minimum points, we don't know, nor do we really care. All right, let's check and make sure these things are true. F is decreasing when x is less than x, which is less than 4. It's decreasing between 0 and 4. So this is 0, and this is 4. And you can see that, in fact, this thing is decreasing, right? This is decreasing. It's going down until we reach that 4. So it looks like this might be the lowest point for something, right? So it is decreasing. So that matches this. So that's true. And F is increasing when x is less than 0. And that is also true. This is where x is less than 0. This is the function increasing. It is going up. So this is increasing. This is decreasing. And then it is also increasing when x is greater than 4. So then it starts going up again. So all of these things are like, yeah, that makes perfect sense. We got the right thing. Here we are. Remember, if we're a little person walking towards the function, give him 2 eyes. He gets here, it is increasing, increasing, increase until, in this case, 0. And then it decreases, decreases, decreases until we get to 4. And then at 4, it gets bigger and it goes and increases again. So, yeah, this is our little sketch. Now, what they want you to do is, from this picture, tell them the degree of the polynomial, whether it is odd or even, and tell them what the leading coefficient is as far as it being positive or negative. All right, so what is the degree of a polynomial? Well, we mentioned that we have 3 x-intercepts, right? So that means we have a cubic, and a cubic is an odd function. And, well, actually, just by looking at the shape, we can just figure this out. This is going down and up. And if you go back to your little table, down and up is odd and positive. So odd and positive. All right? And that's really all that you need for that one. Okay? Awesome. Well, we're done with this lesson, and I'll see you in lesson 4.2. Bye.